Alright, so this video is numerical calculation. We'll be doing it on projectile motion. We're going to be including the air resistance later on. That's just really to show the difficulty that it would be to do on paper. So we just calculate that on the computer here on Python. Alright, so starting with my nice little pretty picture here, we have a cliff that's 10 meters up. There's a ball on top that's being launched, kicked, whatever it is being. At 5 meters per second at the initial angle of 30 degrees, or you can put it in radians, it'd be like 52 or something like that. We have our mass as 0.1. It's pretty light. That's really just to account for whenever we have that air resistance, you can see it, the difference in travel a lot better. The heavier that mass is going to be, the less that air resistance even has to do to it. Also, the lighter that mass travels just a little bit further without that air resistance, so I just figured it'd look better. Alright, so we do have to account for some things, even without the air resistance. We have our gravity, and that initial height and velocity. With that, assuming everything else is pretty constant, we can figure out, like our maximum height. We can figure out our time frame for how long it takes until it hits the ground. And of course, we can also figure out the x, which is the distance from the starting point to the end, how far that ball traveled. I do have a little thing of how to solve for time. I'm not really going to go too far into that just because I'm trying to show off this coding a little bit. Alright. So starting off with our code, we do have our, just descriptions of the two balls. I do have two of them. The first one is going to be omitting the air resistance. The second one will include it. We have our box, the parameters for all that, our gravity vector, the initial velocity, our theta. I have it written in here in radians, although it doesn't matter. These are going to be for the air resistance that'll come in a little bit later with that rho and all that good stuff. Once more, here's some more descriptions of ball 1 and 2, their masses, their vectors. Those are the same because I did want to show the difference with the air resistance. And you'll see the magnitude of the velocity of ball 2 and the normal vector of ball 2. That's, again, just going towards that air resistance. We do have the ball trails, once again, to show the track of those. And down here, I have all the forces acting on them and all that good stuff. I will go ahead and warn for my picture, I do have the balls with a radius and a color. However, I think it's just so small on the scale that they don't go. I will run this real quick without any air resistance. You just see one line. I have both of them the same weight and everything, so they are just going to be together. But yeah, you won't see those balls there at the end, but they are there, I promise you. But let's see now what it would be without, or with the air resistance. Oh, also, note that the positions are also the same. Of course, like I said, they're traveling together. But it does end at 24 meters roughly. I say that because if you look at the last one, 24.5, the y component's negative. That's just because the center of the ball, that's where it touches the ground, whereas instead the edge of the ball. So we're just going to go with the 24 basically. However, when you add that air resistance, alright, so ball 1, you see it's still in the air, ball 2 touched the ground. Ball 1's still in the air because my parameters are for when y is greater than or equal to 0. However, ball 2's already hit the ground, so the program won't continue running because it will break the guideline that I gave it. But notice that the ball 2 position is at 4.6. Before, without it, it was at 24. So it cut off roughly 20 meters almost. That's a pretty strong air resistance, I'd say. That's kind of why I use such a light mass. But yeah, that's that.